Hi everyone! Welcome to part 2 of chapter 16. Today we're going to continue our talk on acids and bases. We're going to start off by looking at the autoionization of water, seeing how water can act as both an acid and a base, and it can actually react with itself. And then we're going to go on to talk about how to calculate the pH, the pOH, the hydronium ion concentration, and the hydroxide ion concentration of a given solution. And then we'll talk a little bit about what makes something a strong acid versus a weak acid, or a strong base versus a weak base. And then finally, we're going to look at how to start calculating the pH of a strong acid. So lots going on today. All right, so we talked last time and we were looking at water, and we said that water was amphoteric, which means that it can act as either an acid or a base. And it just depends on what else it's reacting with, right? Like when it reacted with hydrochloric acid, we saw water behave like a base. And when it was reacting with ammonia, we saw water react like an acid. Since it can, react as both an acid and a base, it makes sense that it can actually go and react with itself. One molecule of water can act as an acid, and another molecule of water can act as a base. So this whole process is called AUTOIONIZATION, where it will make ions by reacting with itself, right? So like if we had two molecules of water, right, we can say, one acted as an acid, one acted as base, so one will produce a hydronium ion and the other will produce a hydroxide ion. And you could also write it like this, right, where water is just kind of splitting into, H plus and OH minus. This, though, is what's actually happening, where it's reacting with itself. Water doesn't split into these two pieces. Anyway, so the whole point of this is that all aqueous solutions will contain both hydronium and hydroxide, and they will be in equal concentrations, right? For every one hydronium, we're making one hydroxide because it came from these two molecules of water that reacted. Therefore, if we know the concentration of one of them, we always know the concentration of the other because they will always be equal in pure water. So at 25 degrees Celsius, which is what we're going to assume all of our reactions are at. We're going to assume all reactions in this chapter are at 25 degrees Celsius unless stated otherwise. Okay, so at 25 degrees Celsius, the concentration of each one of these is 10 to the minus 7th molar. Okay, so this is a very small concentration. So most of the water molecules exist as water, but a small amount of them are undergoing this autoionization. Okay, so again, here it is looking differently, right? So we have a water reacting with a water. One of them will act as a base, right? And so this base is going to accept the proton from the acid, right? And so this bond here is going to break. And so then we're going to end up with the conjugate acid and the conjugate base, okay? And so again, at 25 degrees Celsius, they have equal concentrations. They are 1 times 10 to the minus 7th molar. So if we were to write the mass action expression, we would see that Kw is equal to our hydronium ion concentration times our hydroxide ion concentration. So if we go ahead and plug in that 1 times 10 to the minus 7th molar for both hydronium and hydroxide, we can calculate a value for Kw. So Kw is 1 times 10 to the minus 14. Here, when we were writing Kw, remember we don't include pure liquids. So that would be why we didn't include these water molecules on the bottom, but we did include these aqueous ions on the top. Okay, so Kw is equal to hydronium times hydroxide. This will be a very important equation for you moving forward. I would write it down somewhere. I would also write down this value of Kw. That's going to be important as well. Okay, so like I said, the product, right, so that Kw value, if we multiply H3O plus and OH minus together, is always going to be the same number. This is called the ion product of water. It's Kw. You can think of it as being like the equilibrium constant for water, which is why it has the W, right, or the dissociation constant of water. Okay, it's always going to be 1 times 10 to the minus 14 at 25 degrees Celsius, and like I said, we are going to assume all of these are at 25 degrees Celsius just to make our lives easy. So if Kw is a constant, right, just like our equilibrium constant is a constant, if our, hydronium ion concentration went up, then the hydroxide concentration must go down in order for Kw to remain constant. Okay, these are inversely proportional. One goes up, the other goes down. But what's really nice is since Kw is a constant, if you know one of them, say you knew the hydronium ion concentration, you could go ahead and solve for the hydroxide concentration. All right, so we are going to define acidic and basic solutions based on the concentration of these ions, okay? If we have a neutral solution, okay, that means that our hydronium ion is going to equal our concentration of our hydroxide ion, and that's where we're getting that 1 times 10 to the minus 7, okay? If it is anything other than that, if it's anything other than 1 times 10 to the minus 7, that means you're going to either have more of your hydronium or more of your hydroxide. And whichever one you have more of will determine whether your solution is acidic or basic. So if you have a greater amount of your hydronium ions, okay, so that would be greater than 1 times 10 to the minus 7, which means that hydroxide would be less than 1 times 10 to the minus 7. But if you have more of your hydronium ion, then that's going to be acidic. And if you have more of your hydroxide ion, then that's going to be basic. So you can just see which one you have more of, and that will tell you whether you have an acidic solution or a basic solution. And again, if they are equal, then it's neutral. Okay, so one of the most useful ways to talk about whether something is acidic or basic is pH. Okay, the way that we calculate pH is we take the negative log of the hydronium ion concentration. Okay, so we were just talking about that concentration on the last slide. So if you type that in and you take the negative log of that, then you will get the pH. And this whole thing, this table on the right, is the pH of a bunch of different substances. So like we were talking about your stomach acid last time, right, which was hydrochloric acid, which is very acidic. That's a strong acid. So we will see a very, very low pH. But a lot of other things that you eat or drink have a very low pH as well, like soda. Soda has a really low pH, which is why, oftentimes you'll hear don't drink too much soda. It's really acidic. It can mess with the acidity of your stomach. It can mess with the enamel on your teeth, things like that. Rainwater is slightly acidic, and we'll talk more about that later, but even when it's unpolluted, it is also slightly acidic. Your blood is mostly neutral, but ever so slightly basic. And then we've got some other stuff, right? Milk of magnesia, which is magnesium hydroxide, that's basic. Ammonia is basic. Sodium hydroxide, which we use in lab, is basic, right? So for really low pHs, we are always going to have acids. So if it's low pH, it's going to be acidic, up here at the top. And if it's down here at the bottom, it's going to be basic. And they've put everything in pink, that's acidic. And then everything in blue, that's basic. And neutral, right, would run right through the middle, and that would be at pH equals 7. Okay, so like I said, in order to find the pH of something, you would take the negative log of the hydronium ion concentration. Even if it's basic, we are always going to take the negative log of the hydronium ion concentration to find the pH. Okay, and again, pH of pure water, that's going to be 7 because it's neutral. If we have something less than 7, that's acidic, greater than 7 is basic, exactly 7 is neutral, and then this is going to be really useful. So I'm trying to point out things that are useful here, like this pH equals negative log of the hydronium ion concentration, that one you need to know. And then the reverse of that, right, if we, undo that negative log, that would be 10 to the, right? So we have our hydronium ion concentration is 10 to the minus pH. Okay, and then finally, right, this one we were talking about on the last slide, that's useful as well. Okay, but these are our two new ones, this one and this one. So the pH number is just telling you how acidic or basic something is. If we have a really low pH, that means it's very, very acidic. And the higher the pH is, the more basic it is. Okay, and every pH unit corresponds to a factor of 10 in acidity, right? That's where we're getting that log-based scale. Okay, our normal range is 0 to 14, with 0 being really acidic, 14 being really basic, but we can actually go outside of the range. It can be negative and it can be greater than 14. Those are just like really extreme. So if you have like a really, really concentrated acid, you may have a negative value for your pH, right? Like here, this would be pH is equal to 1 molar. Well, we often work with things that are greater than 1 molar. So that means we are often working with things that have a pH that has a negative pH. Same goes with the bases. If you have, a hydroxide ion concentration that's greater than 1 molar, then you may have a pH over 14. That being said, it's not going to be like 40. It might be like 14.5. Okay, so still going to be somewhere in this range. So we can also express our pH essentially as POH, which is the exact same thing as pH, except you're taking the negative log of your hydroxide ion concentration. Okay, so that's where we're getting the POH versus pH. So pH was the negative log of H3O plus, or, you can think of it as the negative log of H plus. Well, POH is the same thing, except instead you're taking the negative log of the hydroxide ion concentration. Okay, so the scale, though, is going to be exactly backwards. So for pH, this first one, we knew 0 was really acidic, 14 was really basic. Well, POH is going to be exactly the opposite. Okay, 14 is really acidic and 0 is really basic. Okay, so they have different meanings, they have different uses. Okay, POH of water, though, is still going to be 7 because it's going to be neutral. Okay, and then we have all the same kind of things. You have, our concentration of OH minus is 10 to the minus POH, just like our concentration of H3O plus was 10 to the minus pH. Okay, same thing, just a different ion. So by now you're probably thinking, we have a lot of equations going around. Somebody should really make a summary slide. Well, I have. So here's some of the equations that you'll need. So if it's pH, that's the negative log of the hydrogen ion concentration, or the negative log of the hydronium ion concentration. Remember that we use those interchangeably. They mean the same thing. And then POH, same kind of thing, but it's the negative log of the hydroxide ion concentration. pH and POH, we can actually go between them really easily, and pH plus POH is equal to 14, and it's actually 14.00 here. Okay, so if you know one, you can find the other. And then if you needed to find, the hydrogen ion concentration, right, which is the same thing as the hydronium ion concentration, all the same thing, you would do 10 to the minus pH, and then if you needed to find hydroxide, you would do 10 to the minus POH. Lots of equations. And I've got this little map for you here that shows you how to get between, each thing. So let's say you started with H+, and the problem asked you to find the POH. Okay, 2 different ways you could do this, but you just need to follow the arrows. So one way, you could take your H+, and you can take the negative log of that, and you could find the pH. And then once you have the pH, pH plus POH equals 14.00. So you can say, okay, well, if I do, 14 minus pH, then I would get POH, and you would be there. Or you could totally have done it the other way. You could have gone along the top, right? If I know my H+, I can use my KW equation. KW is equal to our hydrogen ion concentration times our hydroxide ion concentration. If I rearrange that, I get this equation, and I can find my hydroxide ion concentration, and then I can take, the negative log of that, and I can find the POH. Okay, so there are more than one ways to do these problems. So when you see me work them out on the lecture worksheet, if you did it a different way, that's okay, as long as you're ending up at the right answer. So let's go ahead and try these, because I think there were a lot of calculations and equations being thrown around. This is posted. So if you want to have this in front of you, or maybe you want to print off the summary slide to help you out, I would do that now, or at least write down the equations so that you have them while you're working. Okay, but I want you to go ahead and pause here and do these practice problems. And then we'll come back and go over them, and then you'll have 3 more practice problems to complete after that. Go ahead, pause here, come back when you're ready. Okay, So for the first one, we're supposed to calculate the hydrogen ion concentration of a solution whose hydroxide ion concentration is 3.6 times 10 to the minus 4 molar. Okay, so we know that relating those, we have Kw, right? Kw is equal to H plus times OH minus. So if we go ahead and rearrange this solution, right, we divide both sides by our hydroxide ion concentration, then we can plug our number in for our H plus and solve for our concentration. And sorry, this should be molarity here. Okay. For the next one, it says to calculate the pH of a solution whose hydrogen ion concentration is 2.3 times 10 to the minus 7th molar. We have an equation that directly relates this. In order to get from pH, or from our hydrogen ion concentration to pH, we are just going to take the negative log. So when we take the negative log of that number, then we're getting 6.64 as our pH. And then similarly, to calculate the pOH from our hydroxide ion concentration, we are just going to take the negative log of that concentration to find our pOH. All right, let's go ahead and try a few more practice problems. Here's some more. Go ahead and pause here and come back when you're ready. Okay, so now we're trying to find pOH from pH. So we have an equation that relates those. pH plus pOH equals 14.00. So we can just go ahead and do 14 minus 9, and that gets us our pOH. For the next one, we need to calculate our pH, and we have our hydroxide ion concentration. Okay, so the first thing that I would do, right, is I would take our pOH, or I would find our pOH. You can do it two different ways. You can do it this way, and I like this way because it involves less scientific notation and we get to whole numbers faster, which I like, but you can do it the other way as well. So the first way would be to take the negative log of that value and find the pOH. And then we know that pH plus pOH equals 14, so we can just do 14 minus our pOH, and that gets us our pH. The other way you could have done it was that, Kw is equal to our concentration of H plus times our concentration of OH minus. So you could have used that to find our concentration of H plus and then taken the negative log of that value, but you would still come up with 6.15 or something really, really close. Okay, for the last one, it says calculate the pOH of a solution whose hydrogen ion concentration 6.9 times 10 to the minus 3rd molar. All right, so similarly, I decided to take the negative log first so that I could find the pH, and then I just do 14 minus our pH to get our pOH. Just like in the last problem, you could have used that Kw, and you could have said, okay, Kw is equal to H plus times OH minus, and you could have, done that and solved for OH minus and then taken the negative log of that. Again, you're still going to come out with 11.84 either way. So again, like I was telling you earlier, there are multiple ways to do all of these problems. You just need to find one that makes sense to you. As long as you're getting the right answer, you're good to go. Okay, let's talk a little bit about strengths of acids and bases. Last time I was talking a little bit about strong acids versus weak acids and strong bases versus weak bases. And the way that we determine whether something is a strong acid or a weak acid or a strong base or a weak base is by the equilibrium constant. Okay, so when this, whether it's an acid or a base, when it reacts with water, what is the equilibrium constant? If our equilibrium constant is extremely large, right? If it almost entirely dissociates, that is going to be a strong acid or a strong base. That's what we're talking about with that strong. We're talking about the strength of the ionization or the strength of the dissociation, right? How much it falls apart in water. So strong acids and strong bases completely dissociate. They are going to have extremely large K values because they form almost entirely products. And then weak acids and bases, though, do not ionize very much. They tend to stay together in water, and they kind of float around more as the acid, as the base, rather than ionizing. Okay, so those would be weak acids and weak bases. So this is what we need here. The smaller the ionization constant, that smaller the value of K, the weaker the acid or the base. because again, we're talking about these strengths of acids with how much they ionize, how much they dissociate. So I've selected a couple. Here are all of your strong acids. Okay, you need to have these memorized. There's no other way to do it. You just need to memorize them. There are 7 of them. Make flashcards or something, right? Find a mnemonic, however you want to learn them, but you need to know the 7 strong acids because then any other acid you see, you know it's a weak acid because it's not one of those 7. So that's the easiest way I can come up with you or for you to do that. Memorize the 7 strong acids. Everything else is a weak acid. I've put a couple weak acids here. There are tons. Lots and lots and lots of weak acids, but I've pointed some of them out that people think are strong acids. So these 3 in particular, people always think they are strong acids, so I would make yourself a mental note that they are weak. Hydrofluoric acid, people think that it is a strong acid because all of the other ones that have bonded with halogens, right, hydrogen and halogen, those are strong acids, but hydrofluoric acid is not. So I make a note of that. It's actually the strongest weak acid, but it is still a weak acid. And then phosphoric acid, people get that one mixed up too. I don't really know why. That is a weak acid, and so is acetic acid. We'll use acetic acid a lot. And I want to point out there are 2 different ways. Well, and there's another one. You could also write it as CH3CO2H. Lots of different ways to write acetic acid. They're all acetic acid, and it is always a weak acid. And then bases. Bases are easier to figure out whether something is strong or weak. If it's got a hydroxide on it, then it's going to be a strong acid because when you put that in water, these are going to behave like ionic compounds. And we know that ionic compounds tend to dissociate in water. So any of those that you stick into water, they will completely dissociate. We're going to say those are strong acids. And then if it has a nitrogen, those are going to be our weak acids. So remember when we were just talking about Bronsted-Lowry bases, we said that they needed to have a lone pair. Well, this lone pair is on the nitrogen, and it will go and try and grab hydrogens from acids. Okay, so these are weak acids, and like I said, they mostly contain nitrogen. All right, another way of expressing the strength of an acid or base is the pK. And if it's an acid, we're going to say pKa, and if it's a base, we're going to say pKb, right? To keep it to keep them straight. This P in the front, we keep seeing like pH, POH, pKa, pKb. We'll see pKw. Those are the ones I can think of right now. Anytime you see the P, think of the P as meaning take the negative log. So like pH literally means take the negative log of the hydrogen ion concentration. Take the negative log of the hydroxide concentration. Take the negative log of the Ka. Take the negative log of the Kb, right? Over and over and over. So that is how, right? See like pKa, take the negative log of the Ka. pKb, take the negative log of the Kb. And then you can also do the reverse. If you have if you have pKa, you can do 10 to the minus pKa to find the Ka, or 10 to the minus pKb to find the Kb. They are going to behave just like the concentrations of the ions that we did before when we went between our concentration and our pH. It's going to be the same to go from the Ka to the pKa or the Kb to the pKb. Okay, so when we're talking about the strengths of the acid, remember a strong acid is going to have a very large Ka. And in fact, sometimes it is so large that they don't even measure it. They just write that it's very large, right? Because it's so, the dissociation is so complete. It goes to completion. But the larger this Ka, right, the way the math works out, the smaller the pKa. And I like to think of it as, okay, well, we know a strong acid would have a really low pH. So if it's going to have a really strong acid, it makes sense that it should have a small pKa because it would have a small pH. So I relate those. Okay, and this is all because pKa is the negative log of that Ka. That's how it works out mathematically. Same thing with a base. If it's a base, it's going to have a really large Kb, which means it's going to completely dissociate, and it's going to have a very small pKb because it's related to the pOH scale. Okay, so pKa or Ka both can tell you about how strong or weak the acid is. or the base. Okay, so when an acid dissociates, right, our acid is going to react with our water to produce our conjugate base and our hydronium ion. And when we write our Ka expression, right, our equilibrium expression, we're going to put, our products over our reactants, just like we did when we were doing equilibrium. Just remember, you never, ever, ever include water in your equilibrium expression because we will never include pure water, pure solids, pure liquids, anything like that in our Ka expressions. You could also have written it like this. Either way, forgot the H there. Either way is totally fine because we know that this is implied as H3O+. So if you want to write it shorthand, that's okay. They mean the same thing. And sorry, I should have introduced this HA here. This is just some generic acid. This means that there is a hydrogen on stuff. And then this is the stuff without the hydrogen. Okay, the hydrogen has moved over and is now hanging out with the water. It's just to show any generic acid so that we can see the transfer of that hydrogen to the water, leaving behind the conjugate base. All right, so like I was talking about, strong acids pretty much donate all of their hydrogen ions. There may be like literally 1 or 2 molecules out of millions that didn't, but pretty much they all dissociate. So we are going to just say they are 100% ionized in water. They don't form an equilibrium, which is why we are getting a single-headed arrow. They are a strong electrolyte. They completely dissociate, totally all in ions in the water. Okay, so when that happens, we can treat our concentration of H3O+, right? Because our goal a lot of times is to find the pH. So we need to know what the concentration of H3O+ is because pH is equal to the negative log of our hydronium ion concentration. So we need to know what that concentration is. Well, most of the time when we're doing one of these types of problems, they will tell you like, okay, well, maybe this hydrochloric acid was 2.0 molar. And I stuck it in there. Okay, so when I put my 2.0 molar hydrochloric acid into the water, it completely broke apart. And when it does that, if this was 2.0 molar, let's think about an ice table. Okay, so if this was 2.0 molar, and we don't have any water, and then, well, I mean, we don't care about water. When this reacts, right, all of this is going to react, which is going to produce 2.0 molar of each one of these. Okay, so you can think of our 2.0 as being like minus X plus X plus X. So our initial concentration of our acid, because it completely dissolves, is going to be equal to our hydronium ion concentration at the end, right, at equilibrium. Well, at the end of our reaction, not our equilibrium, at the end of our reaction. So when we go through and we calculate our pH, we don't actually need to do an ice table because our H3O+ concentration is going to be equal to our initial concentration of our strong acid because it completely dissociates, which is really handy. That makes our calculations a lot easier because we don't need to do an ice table. Okay, so strong acids completely dissociate in solution. So again, that means they are going to have an extremely large Ka. They make a lot of products and then don't essentially have any reactants. So we would say that this is product favored because it's going to make almost entirely products. So here's some of them, right? Here's our 7 strong acids. So we have our acids, we have our conjugate bases, and again, remember our conjugate base just means that we've lost a hydrogen. So we lose our H and we gain a negative charge from losing that H. And if you look at our Ka values, they don't even list them. They're very large. They don't make an equilibrium. It doesn't matter. They're very large. So as you can see, we're not going to do any kind of ice table calculations because we don't have any K values. So if you'll recall from earlier, we were talking about the fact that water will, ionize with itself. So 2 water molecules can react and they'll produce some OH- and some H3O+. So in reality, when we put that strong acid in the water, we have some H3O plus coming from the acid, but some also coming from the water reacting with itself, okay? But when we have a strong acid, because they are contributing so many H3O plus ions, right? So many hydronium ions, the contribution of the water with those, those couple H3O plus, it's negligible, right? It doesn't make a difference because that ionization constant of water is not going to be enough to really mess with our calculations at all, okay? That adding our acid shifts that KW equilibrium so far that it doesn't matter how much is coming from the water. So that's why, again, we're just going to use our initial concentration of our acid as our H3O plus concentration, so we can directly take the negative log of our initial acid concentration to find our pH. So here's a practice problem. So it says calculate the pH of a 0.25 molar solution of nitric acid. So if you think you know what's going on, go ahead and pause here and try this one out. Once you're done, unpause and come back and see the answer. Okay, so again, nitric acid is one of our strong acids. So when we put nitric acid into water, it's going to completely dissociate. Okay, so here's our nitric acid. It reacts with water. It's going to make hydronium ion and nitrate. Again, single-headed arrow, no equilibrium, okay? All of it's going to dissociate. So what that means is that our initial concentration of nitric acid is going to be equal to our equilibrium concentration of our H3O+. So we can just directly take the negative log of this initial concentration. Okay, and so that's going to be 0.602. Very, very, very acidic. Okay, so for strong acids, our calculations are really easy. Whatever concentration they give you in the problem, take the negative log of it. That's the pH. Done. Maybe they might ask you also for the pOH or, the hydroxide ion concentration, but if they ask you for just pH, negative log, done, because it completely dissociates. And that is the end of today's lecture. Next time, we are going to get into weak acids, strong bases, and weak bases. There is going to be a lot of math. It's going to be a lot of ICE tables in this next lecture. So make sure you bring your A game and you have your calculator ready. In the meantime, practice all of these calculations from going from H plus to OH minus to pH to pOH, right? Make sure you know how to do all of those things because in the next lecture, I'm going to assume that you have done that practice and that it's really easy for you. I'm also going to assume that you are an expert at equilibrium concentrations, okay? Or at equilibrium calculations. So make sure you are really, really solid on chapter 15 because we are going to use it moving forward in this chapter. So get lots of practice, keep working on the lecture worksheet problems. If you have any questions, please send them my way. Otherwise, I will talk to you guys next time.